Okay, well, I'd like to finish up section 11.7 here, which is a strategy for testing series, and we're just looking at a bunch of series, and they're not telling us use this technique or that technique. You know, we need to figure it out for ourselves. Okay, so I got 3 more examples here. Let's see, in this next example, we have the summation as n equals 1 to infinity of negative 1 to the n times n divided by n squared plus 2. Okay, the negative 1 to the n kind of hints at the fact that it'd be an alternating series test. Okay, if I didn't want to try the alternating series test, then maybe the ratio test would be another option, but that I see the negative 1 to the n there. Okay, so there's 2 things that have to happen for the alternating series test. First of all, the limit as n approaches infinity of the sequence disregarding the negative 1 to the n term has to be 0, and then the terms also have to be decreasing. Okay, so we got the limit as n approaches infinity of n divided by n squared plus 2. Let's see, we can use L'Hopital's rule, or if I just multiply the top and bottom by 1 over n squared, then I have the limit as n approaches infinity of 1 over n divided by 1 plus 2 over n squared. And as n is approaching infinity, we get 0 divided by 1, that's 0. Of course, I want to make sure I'm not dividing by 0 here. So that's condition 1. Condition 2 says that the terms are decreasing. Okay, and we'll just go back to Calc 1 for the moment, and we use the first derivative test. So if I let the function f of x be x squared divided by x squared, x divided by x squared plus 2, then f prime of x, using the quotient rule, that'd be the bottom is x squared plus 2 times the derivative of the top, that's 1, minus the top, that's x, divided by the derivative of the bottom, that's 2x divided by the denominator squared. Okay, x squared minus 2x squared is minus x squared. So I'm looking at 2 minus x squared up top, divided by x squared plus 2 squared down under. Okay, now in the denominator, we're always going to have a positive number no matter what. Okay, because we're squaring this expression there. Okay, so this is going to be less than 0, meaning that the terms are going to be decreasing when the numerator is less than 0. Okay, so I got 2 minus x squared less than 0, and if I solve this inequality, add x squared to both sides, I got x squared greater than 2, so then take the square root of both sides. X is greater than root 2, or x is less than negative root 2. Well, we're not looking at anything that's negative here for the n values there. Root 2 is about 1.41, etc. Okay, so the terms don't decrease right away, but they do decrease, very quickly at 1.12. So the function f of x is decreasing on the interval root 2 to infinity. Okay, and you could say that the n plus first term is always going to be less than the nth term when n is greater than or equal to 1. Okay, so the terms decrease. Because the limit gave me 0 and the terms decrease, I can say that the series is a convergent series. Okay. Let's look at another example here. So I got the summation as k equals 1 to infinity of 2 to the k times k factorial divided by k plus 2 factorial. Okay, I see these factorial signs. I've also got a 2 to the k. That kind of gives me a hint that it's going to be a ratio test type situation. Okay, so the absolute value of a sub k plus 1 divided by a sub k, that's equal to a sub k plus 1, replace the k's with k plus 1's. You got 2 to the k plus 1 times k plus 1 factorial divided by k plus 3 factorial. And then you're dividing by a sub k, or multiply by the reciprocal of a sub k. So if I flip the a sub k there, I'm multiplying this by k plus 2 factorial divided by 2 to the k times k factorial. Okay, so this is what I got to simplify here. 2 to the k plus 1, the same as 2 to the k times 2. 2 to the k cancels with 2 to the k down here, so I'll be left with 2 up top. K plus 1 factorial, that's the same as k plus 1 times k minus 1 times k minus 2 times right down the list. And I'm dividing that by k factorial, which is the same as k times k minus 1 times k minus 2 times right down the list. K factorial of the terms will cancel with part of the k plus 1 factorial of the terms, and that would just leave me with k plus 1 up top. And I've got k plus 2 factorial divided by k plus 3 factorial. Okay, k plus 2 factorial, that's the same as k plus 2 times k plus 1 times k minus 1 times k minus 2, etc. And when I cancel those, I'm going to be left with just a k plus 3 term in the denominator there, because all k plus 2 factorial of these terms cancel. So that gives me 2k plus 2 divided by k plus 3. I can lose the absolute value bars. K is already a positive number. Okay? So then the limit as k approaches infinity of 2k plus 2 divided by k plus 3, I can use L'Hopital's rule if I want, or if I multiply the top and bottom by 1 over k, I'm looking at the limit as k approaches infinity of 2 plus 2 over k divided by 1 plus 3 over k, which gives me 2. Okay, 2 is bigger than 1. And now remember with the ratio test, if I get a number that's less than 1 but still positive, I'm convergent. If I get a number that's bigger than 1, like I did here, then I've got a divergent series. I guess that'd be my answer. And if we're equal to 1, then the test failed, and so you got to try something else there. Okay, no conclusion could be made from the test if I had a limit equal to 1. Okay, so this is a divergent series. Here's another example. So what if I had the summation as n equals 1 to infinity of 6 to the n divided by 5 to the n minus 1? Okay, well, let's see. So if I use the comparison test, like what if I didn't have the minus 1 there in the denominator? Okay, what if I just had 6 to the n divided by 5 to the n, or 6/5 to the n? Well, if I'm subtracting 1 in the denominator, then the left side is always going to be bigger than the right side, right? If I had a denominator of 3, like 1/3 or something like that, that's going to be bigger than 1/4. Okay? Yeah, so the left side is always going to be bigger than the left side is always going to be bigger than the right side. The right side gives me 6/5 to the n, and this is for n greater than or equal to 1. And this is a geometric series. So the sum as n equals 1 to infinity of 6/5 to the n, that diverges because the r value, 6/5, is greater than or equal to 1. Okay, and this comparison will work because, I've got a divergent series here on the right, and I'm comparing that term by term to something that's bigger than that. Okay, well, then I know that the original series is also going to be divergent. Okay, so the summation as n equals 1 to infinity of 6 to the n divided by 5 to the n minus 1 diverges by the comparison test. Okay, section 11.7 is really important. Okay, again, because they're not telling you what technique to use. That's we have to figure out on our own which technique is appropriate. Okay, be sure to look at the homework that's in section 11.7. That's really important stuff. Okay, we have 3 more sections left, so I'm going to start in on 11.8 in the next video there.